conditions.
Thank you, Michael. So this work is about discovering equalities between inputs and outputs of programs. And this is joint work with colleagues and former colleagues from Prove and Run and from INRIA. And it's actually part of a larger industrial project whose goal is to formally verify an OS microkernel. This microkernel is called proven core, and we have formally proved that it ensures a form of spatial isolation between processes. It's been developed at Prove and Run, which is a small company located both in Paris and on the French Riviera. And at Prove and Run, we develop trustworthy, reliable software with the help of formal methods. And this is one more example that the techniques and the ideas that you guys from the Purple community have been developing for the last 40 years are actively used in the industry, and not just at Facebook and Microsoft. So let me tell you about the strange dream I had last night. Somebody was asking me to program a new version of Hotcrap and formally verify it. So I started writing down some type definitions. So definitely in the state, there should be a data structure to hold the list of authors, another one to hold the list of submitted papers, and another one for reviewers. And papers were themselves a large data structure with at least one field that I remember, which must contain an identifier. And somehow these identifiers for papers had to be unique. And I wrote down also a function to add a new reviewer to the state. And somehow I had to preserve to show the preservation of the uniqueness of paper IDs by adding new reviewers to the system. And in my dream, it was very easy, trivial, because, well, the property I'm interested in only looks at one field of the state, the papers field, and the add reviewer function can only modify a different field of the state, the reviewers field. So of course, the property is preserved. But what happens when you actually need to perform a mechanical proof of such properties? How easy can it be? Well, so here's a more detailed proof sketch. So the first step is to show that the property of uniqueness of IDs is actually stable under changes of the state that preserve the papers field. The second step is to show that the add reviewer function only modifies the reviewers field. That is to say, it preserves all the other fields. And finally, you have to show that preserving all the other fields also means that, in particular, you preserve the papers field. So what do we have so far? We have found a relation on states that preserve the property. We have found a second relation that abstracts the behavior of the function we're interested in. And we have just performed an inclusion sec showing that the change performed by the function is actually compatible with the preservation of the property. And that's actually a generic reasoning rule. You could call it a modus ponens for invariant preservation if you like. It probably belongs to folklore, but it's nonetheless very useful. And we used it a lot during the proof of proven core. In practice, what we noticed is that the relations R and F are actually pretty large, especially when the state of the system is large, which makes them very painful to write. What we also noticed is that the proofs of the premises can be quite large, but pretty easy. So quite naturally, we asked ourselves whether we could automate any of these steps. So let's look at the first premise. Well, it deals with finding a relation that preserves a property. To find such a relation, you need to answer the question of which parts of the state are actually read by your property. And that's a well-known problem that we know how to solve using a simple dependency analysis. And if you're interested in a dependency analysis that supports algebraic data types, I invite you to have a look at the paper written by my co-authors a few years ago. The second premise is about finding a relation that abstracts the behavior of the function. To find such a relation, you need to understand which parts of the state are modified by your function, or if you prefer, which parts are actually preserved by your function. That's again a well-known problem. It's a frame condition. It's finding a frame condition, and this is the very topic of this talk. In this talk, we develop what we call a correlation analysis, which is an equality analysis that supports algebraic data types. So more precisely, we have developed an inter-procedural static analysis that infers inputs and outputs, equalities between inputs and outputs of programs for programs that are expressed as control flow graphs of a Y language, which is strongly typed, supports algebraic data types, functional arrays, does not support pointers, and only supports first-order functions. So this is a very restrictive setting, but it's actually expressive enough to program a feature-rich operating system kernel. And to develop this, to actually perform this analysis, we introduce a new abstract domain that we call correlations. And the goal of this work is to discharge a lot of proof obligations that arise when you perform interactive verification of programs. So how does it work? Well, here is a control flow graph with the entry point in green. At every program point, the analysis is going to infer a relation between the values at the entry point and the values at that program point. And to go one step further, we consider the transfer function of the current instruction, and we compose it with the relation we've obtained so far. And I really mean composing in the sense that this is the relational composition. And at the end of the analysis, what you get is a relation between the values at the input and the values at the output of your programs. And that's called a function summary, and this is exactly what you need to define an inter-procedural static analysis. And these function summaries look like a map that, for every input X and output Y, associate a correlation C. So what are these correlations exactly? Well, correlations are binary relations over values. Values are composed of basic values that could be booleans, integers, etc. Record values and constructors applied to values. And correlations are composed of three basic relations. The full relation that is used when you don't have any information whatsoever between values. The equality relation that is used when values are the same. And the empty relation that is used to deal with impossible cases. And then we extend these relations for records and invariants. And you can see that there is this annotation with a side L or R that describes which value in the relation is actually deconstructed. So, for instance, record correlations will relate a record on one side with another value on the other side, and a variant correlation will relate a variant value on one side with some other value on the other side. So let me try to explain that better. A record correlation relates a left-sided record correlation relates a record on left-hand side when the first projection of the record is related to W on the right using the first correlation, and the same for the second projection and second correlation, etc. And all these constraints are composed using intersection. And here we use intersection because somehow all the fields are related to the value W. And instead of a left-sided correlation, if you consider a right-sided correlation, well, simply flip the whole figure from left to right. Now for variance, it's dual to record correlations. You just have to use union instead of intersection. So more formally, we define in the paper a type-indexed interpretation. We interpret the correlation as binary relation on values. Here's the formula, but I told you everything about it already. And if you want some more information, I invite you to look at the paper. But you probably deserve an example. So here is a program P that takes a record as input and that performs a permutation of the fields and returns this permutated record as output. And it can be described using this correlation. So here it is typeset as a matrix. And if you look at the first line, well, it tells you that the field F has actually moved to the field G in the output. The second line tells you that the field G of the input was moved to the field H in the output, and well, it's very similar for the last line. What about an example with variance now? Here is a function that takes a variant as input and produces some possibly non-deterministic variant as output. So if you look at the first line of the correlation that describes its behavior, you can look that it corresponds to the first line in the pattern matching case. It tells us that A of y is actually transformed into B of y. The presence of the EQ correlation is interesting here, telling us that the arguments are the same. And the use of bottom for A and C tells us that no A and no C can be produced by the function. The second line is very similar to the first one. And finally, the last line tells us that effectively, either you can produce A with the same parameter, or you can produce B with an unknown parameter, and you can never produce C. So in the paper, we define operations like the inclusion, the union, and intersection and correlations, and we prove that they are correct in the sense that they are over approximations of their relational counterparts. And interestingly, they are defined using a projection operator, which allows us to define them in a pointwise manner. I won't be able to walk you through the details, so please have a look at the paper. We also define a composition operator, which is the central operation on correlations. For this operation, bottom is absorbent, the equality is a neutral element, and to compose record correlation together, well, you use a formula that looks like a dot product and a dual dot product for variant correlations. And again, we have proof sound in the paper and in Coq that this operator is a safe abstraction of the relational composition of relations. So you're going to find a lot more in the paper, the definition of the transfer functions that define the analysis, how we extend the analysis to handle functional arrays, we give implementation details, and also how we random tested the implementation of the transfer functions. So we applied the analysis to the proven core development. It's an interesting example for at least two respects. First, because the state of the system is quite large. If you consider the type definition of the state as an abstract syntax tree, it's approximately 240 leaves. So having an automatic way to infer equalities is, in this case, much more than a convenience. It's a must-have. And proven core is also interesting for a second reason. The development itself is quite large, about 5,800 lines of code. And so we were quite happy that the analyzer infers equality for the whole development in less than 15 seconds. And what is really interesting is how precise are the results. And to do that, we considered the 28 system calls of proven core and with 15 invariants, and we tried to apply the reasoning rule I introduced at the beginning, and we tried to discharge the premises using the static analysis I just described. And it turns out that 68% of the preservation lemmas are automatically discharged. And even more interesting is the distribution of the success rates. So here is the graph of the success rates per system call. So you can see that a very large majority of them has either good or excellent results. Only 4 of them are actually have poor results. So I don't know if you can see them in the back, but these are the exit, kill, and fork system calls, which are actually very complex system calls and that required most of the efforts during the formal proof. So in the paper, we compare our work with other work. It's strongly related to, relational shape analysis is a recent work that is strongly related. So we do not support heap and pointers, but on the other hand, they do not support variants. The concurrence closure abstract domain is also very close to what we did. Unfortunately, they do not support variants, and that doesn't seem very easy to extend this work with variants. So to sum up, we have developed a correlation analysis whose goal is to infer equalities between inputs and outputs. To our knowledge, it is the first equality that handles algebraic data types. It has a simple meta theory that we formalized in Coq, and we think it really helps proof engineers focus on the interesting parts of proofs. And I'm looking forward to your questions.
So to start off, we have a question on Slido. Could your correlation analysis be used with relational numerical abstract domains?
So I've showed you that correlations are made of 3 basic correlations, the 3 first ones. I think that it's fairly possible to extend these correlations with new cases that would be relational domains to handle numeric invariants like octagons. I haven't done it, but I'm confident it's fairly doable.
Is your abstract domain of finite height? I have the impression that can grow forever, and you have no example where it grows forever?
Yes, we have.
So what do you do?
So in that case, we use widening to
And then from Slido, we have, you track equalities for input-output relations. Can it also work for inequalities?
I think it's very close to the first question I answered. I think I'm going to give the same answer that I gave for the first question, which is we can very possibly add a support for new relational domains, which could support inequalities.
Any other questions? Okay, let's thank the speaker.